Hello dear learners, welcome back to our online tutorial. So we are going to cover few topics of our unit number 1. The topics which we are going to cover are algorithm complexity and big O notation. Algorithm complexity. So in computer technology, whenever we say complexity, so that means we are focusing on two parameters, that is time and space. Therefore, complexities are categorized as time complexity and space complexity. So, complexity is actually a measure by which we can determine the efficiency of an algorithm. So, that we have to be very much clear about that. So, whenever we are saying complexity of an algorithm means we are going to check the efficiency of an algorithm in terms of time and space. So, again I am repeating. So, complexity of an algorithm is actually measuring the efficiency of an algorithm in terms of time and space. Now, time complexity. Time complexity of an algorithm represents the amount of time required by the algorithm to execute to completion. So, it's very easy to understand. So, it represents the total amount of time required by an algorithm to run till its completion. And it is calculated by taking frequency count of the statements. That is how many times the statements are executed. And it is also very practical that we can't calculate time complexity or time requirement just by taking a watch or keeping time. We can't measure time just by taking watch or some counter. So for that, we must have some theoretical analysis for that. So what theoretical analysis expert says, okay, we should take frequency count of a statement. So if two algorithms are given for the same task, the algo which is having lesser frequency count is efficient as compared to algo which is taking more frequency count. For example, over here we have two algorithms, A equal to A plus 1. So A equal to A plus 1 is a simple statement, assignment statement, where we are assigning A plus 1 to A. So this statement is a single or simple statement. It is not bounded by any loop or any condition or anything. So it will be executed only once. So time complexity will be 1. Similarly, if we have algorithm 2, over here I have a for loop for I equal to 1, I less than equal to n, I plus plus. Means my loop is starting from 1 and then it is going up to n. And we have a statement inside loop. The statement is A equal to, you can see A equal to A plus 1. So this statement will be executed n times. So time complexity is n. So this is how we calculate time complexity. So it is very clear from the example that while calculating time complexity, we have to find out how many times our statements are getting executed. For example, in the first algo, it is executed once, so time complexity is 1. In the second algorithm, it is executed n times, so complexity is n. Next slide. Space complexity. Space complexity of an algorithm represents the amount of space required by the algorithm to execute to completion. Similar to time, definition is very much similar. In time complexity, we measure time requirement, and in space complexity, we measure space requirement. And definitely it should be less. For an efficient algorithm, the time and the space requirement should be less. The space needed by an algorithm is equal to the sum of following two components. First is fixed part, that is the space required to store certain data and variables, constants, etc. that are not dependent on the size of the problem. So these are the fixed memory requirement, for example, declaration of variables, constants, etc. Another requirement is the variable part, size of which varies and depends on the size of the problem. For example, recursion, where we have repeated function call. Similarly, dynamic memory allocation, which we'll see in linked list. because in any numerical we are allocating memory at the runtime on some conditional basis. So for such kind of algorithms we can't determine space complexity in a static way. Those comes under variable part. Therefore, while computing space complexity requirement, we have to identify a fixed part as well as the variable part of memory allocation. And next is, over here we have a mathematical denotation of that. So space complexity requirement is a plus sp of I, where a is treated as the fixed part and s of I is treated as a variable part of the algorithm, which depends on the instant characteristic I. At particular instance, what are the static requirements and what are the dynamic requirements? So that is the finally our space requirement. Note: it is not possible to determine exact time and space requirement of an algo because it depends on architecture, both software as well as hardware of machine. So our time and practically time and space complexity varies from system to system. Therefore, analysis is totally theoretical or ideal. Big O notation. Big O notation is a theoretical measure for calculating time and space complexity, where we perform calculations and at the end we come to some equation or some function. Now, using that function or equation, we can describe or define the complexity of our algorithm. For example, we are saying some function f of n equal to O of g of n, means it is less than some constant multiple of g of n. This time complexity of function f of n equal to O of g of n. The notation to read is f of n is big O of g of n. It is a measure of how well a computer algorithm scales as the amount of data involved increases. So this is how we can actually pinpoint our algorithm, or we can identify the behavior of our algorithm if our data increases in a scalar manner or in a very rapid manner. Always, while determining complexity, it is determined by the in terms of number of elements or size of inputs, that is n. And we have to remember, the bigger the value of big O notation, output will be slower. Means the value which we get after analysis should be less, which we have already pinpointed, already discussed. For an efficient algorithm, time and space requirement should be less. So if our big O value or big O notation value is more, means time or space requirement is more. So output will be slower. So smaller the value of big O notation, output will be faster. So while measuring time or space complexity, there are three types of measurement: best case, worst case, and average case. In the best case, if it is for time complexity, algorithm will take very less time. In the average case, it will take moderate time. In the worst case, it will take more time. Examples are: one example of constant time is given. In this algorithm, I have two statements, a equal to 2 and a equal to a plus 1. Both are simple statements and both require single execution step. So complexity will be O of 1, O of 1. So total complexity is O of 1 plus O of 1 equal to 2 times O of 1. So finally we get complexity O of 1, ignoring the constants. We consider only the O of 1 term, ignoring the outside constant. Similarly, for linear time calculation, for example, we have a for loop in this algorithm: I equal to 1, I less than equal to n, I plus plus. This loop will run n times. A equal to a plus 1 is a simple statement, O of 1. But this is O of 1, but it is running n times, so it will become n into O of 1. So finally it will become O of n. The same statement running n times. Next example of quadratic time. Based on the value of big O notation, the name is given. Constant time, linear time, quadratic time. In this example, I have two loops for I equal to 1, I less than equal to 1, I plus plus. This loop will run n times. Again, we have a nested for loop j equal to 1, j less than equal to n, j plus plus, which will also run n times. And inside this loop, I have a single statement a equal to a plus 1, which has a complexity of 1. So this statement is having complexity s of 1, but it is inside two loops. So complexity will become n into O of 1. So finally it will become O of n square. The common big O notations are given over here. These are the common big O notation function and their name. 1. Constant time, log of n, logarithmic time. Simple n means linear time, and log n, logarithmic linear time. If we are having in terms of n square, it is quadratic time. If our equation or the function is in the form of cube, it is cubic time. If it is in the form of 2 raised to n, like exponential form. So, in this video, we have discussed what is complexity and how to calculate time and space complexity using big O notation, and what are the common functions of big O notations. Thank you very much.